A solar panel is a set of solar photovoltaic modules electrically connected and mounted on a supporting structure. A photovoltaic module is a packaged, connected assembly of solar cells. The solar panel can be used as a component of a larger photovoltaic system to generate and supply electricity in commercial and residential applications. Each module is rated by its DC output power under standard test conditions, and typically ranges from 100 to 320 watts. The efficiency of a module determines the area of a module given the same rated output. An 8% efficient 230-watt module will have twice the area of a 16% efficient 230-watt module. A single solar module can produce only a limited amount of power. Most installations contain multiple modules. A photovoltaic system typically includes a panel or an array of solar modules, an inverter, and sometimes a battery and/or solar tracker and interconnection wiring. Theory and construction. Solar modules use light energy from the sun to generate electricity through the photovoltaic effect. The majority of modules use wafer-based crystalline silicon cells or thin-film cells based on cadmium telluride or silicon. The structural member of a module can either be the top layer or the back layer. Cells must also be protected from mechanical damage and moisture. Most solar modules are rigid, but semi-flexible ones are available, based on thin-film cells. These early solar modules were first used in space in 1958. Electrical connections are made in series to achieve a desired output voltage and/or in parallel to provide a desired current capability. The conducting wires that take the current off the modules may contain silver, copper or other non-magnetic conductive transition metals. The cells must be connected electrically to one another and to the rest of the system. Externally, popular terrestrial usage photovoltaic modules use MC3 or MC4 connectors to facilitate easy weatherproof connections to the rest of the system. Bypass diodes may be incorporated or used externally, in case of partial module shading, to maximize the output of module sections still illuminated. Some recent solar module designs include concentrators in which light is focused by lenses or mirrors onto an array of smaller cells. This enables the use of cells with a high cost per unit area in a cost-effective way. Efficiencies. Depending on construction, photovoltaic modules can produce electricity from a range of frequencies of light, but usually cannot cover the entire solar range. Hence much of the incident sunlight energy is wasted by solar modules, and they can give far higher efficiencies if illuminated with monochromatic light. Therefore, another design concept is to split the light into different wavelength ranges and direct the beams onto different cells tuned to those ranges. This has been projected to be capable of raising efficiency by 50%. Currently the best achieved sunlight conversion rate is around 21.5% in new commercial products, typically lower than the efficiencies of their cells in isolation. The most efficient mass-produced solar modules have power density values of up to 175 Wm2. A research by Imperial College, London has shown that the efficiency of a solar panel can be improved by studying the light-receiving semiconductor surface with aluminum nanocylinders similar to the ridges on Lego blocks. The scattered light then travels along a longer path in the semiconductor, which meant that more photons could be absorbed and converted into current. Although these nanocylinders were used previously in which aluminum was preceded by gold and silver, the light scattering occurred in the near-infrared region and visible light was absorbed strongly. Aluminum was found to have absorbed ultraviolet part of the spectrum, and the visible and near-infrared parts of the spectrum were found to be scattered by the aluminum surface. This, the research argued, could bring down the cost significantly and improve the efficiency, as aluminum is more abundant and less costly than gold and silver. The research also noted that the increase in current makes thinner film solar panels technically feasible without compromising power conversion efficiencies, thus reducing material consumption. Efficiencies of solar panel can be calculated by MPP, maximum power point, value of solar panels. Solar inverter convert the DC power to AC power by performing MPPT process. Solar inverter sample the output power, IV curve, from the solar cell and apply the proper resistance to solar cells to obtain maximum power. MPP, maximum power point, of solar panel consist MPP voltage, VMPP, and MPP current, IMPP. It is a capacity of the solar panel, and the higher value can make higher MPP. Micro-inverted solar panels are wired in parallel, which produces more output than normal panels which are wired in series, with the output of the series determined by the lowest performing panel. Microinverters work independently, so each panel contributes its maximum possible output given the available sunlight. Crystalline silicon modules. Most solar modules are currently produced from silicon photovoltaic cells. These are typically categorized as monocrystalline or polycrystalline modules. Thin film modules. Third-generation solar cells are advanced thin-film cells. They produce a relatively high-efficiency conversion for the low cost compared to other solar technologies and were developed by Jacob S. Gibbs and Brinsley Colbert. Rigid thin-film modules. In rigid thin-film modules, the cell and the module are manufactured in the same production line. The cell is created on a glass substrate or superstrate, and the electrical connections are created in situ, a so-called monolithic integration. The substrate or superstrate is laminated with an encapsulant to a front or back sheet, usually another sheet of glass. The main cell technologies in this category are CDTE, or a C, or a C plus C tandem, or CIGS. Amorphous silicon has a sunlight conversion rate of 6 to 12%. Flexible thin film modules. Flexible thin film cells and modules are created on the same production line by depositing the photoactive layer and other necessary layers on a flexible substrate. If the substrate is an insulator, then monolithic integration can be used. If it is a conductor, then another technique for electrical connection must be used. The cells are assembled into modules by laminating them to a transparent colorless fluoropolymer on the front side and a polymer suitable for bonding to the final substrate on the other side. The only commercially available flexible module uses amorphous silicon triple junction. So-called inverted metamorphic multi-junction solar cells made on compound semiconductor technology are just becoming commercialized in July 2008. The University of Michigan's solar car that won the North American Solar Challenge in July 2008 used IMM thin-film flexible solar cells. The requirements for residential and commercial are different in that the residential needs are simple and can be packaged so that as solar cell technology progresses, the other baseline equipment such as the battery, inverter and voltage sensing transfer switch still need to be compacted and unitized for residential use. Commercial use, depending on the size of the service, will be limited in the photovoltaic cell arena, and more complex parabolic reflectors and solar concentrators are becoming the dominant technology. Flexible thin-film panels are optimal for portable applications as they are much more resistant to breakage than regular crystalline cells, but can be broken by bending them into a sharp angle. They are also much lighter per square foot than standard rigid solar panels. The global flexible and thin-film photovoltaic market, despite caution in the overall PV industry, is expected to experience a CAGR of over 35% to 2019, surpassing 32 GW according to a major new study by Intertek Pyra. Smart solar modules. Several companies have begun embedding electronics into PV modules. This enables performing maximum power point tracking for each module individually, and the measurement of performance data for monitoring and fault detection at module level. Some of these solutions make use of power optimizers, a DC-to-DC converter technology developed to maximize the power harvest from solar photovoltaic systems. As of about 2010, such electronics can also compensate for shading effects, wherein a shadow falling across a section of a module causes the electrical output of one or more strings of cells in the module to fall to zero, but not having the output of the entire module fall to zero. Module performance and aging. Module performance is generally rated under standard test conditions, irradiance of 1000 with mass squared, solar spectrum of AM 1.5 and module temperature at 25 AA degrees Celsius. Electrical characteristics include nominal power, open circuit voltage, short circuit current, maximum power voltage, maximum power current, peak power, WP, and module efficiency. Nominal voltage refers to the voltage of the battery that the module is best suited to charge. This is a leftover term from the days when solar modules were only used to charge batteries. The actual voltage output of the module changes as lighting, temperature and load conditions change, so there is never one specific voltage at which the module operates. Nominal voltage allows users, at a glance, to make sure the module is compatible with a given system. Open circuit voltage or VOC is the maximum voltage that the module can produce when not connected to an electrical circuit or system. VOC can be measured with a meter directly on an illuminated module's terminals or on its disconnected cable. The peak power rating, WP, is the maximum output under standard test conditions. Typical modules, which could measure approximately 1 x 2 meters or 2 x 4 feet, will be rated from as low as 75 watts to as high as 350 watts, depending on their efficiency. At the time of testing, the test modules are binned according to their test results, and a typical manufacturer might rate their modules in 5-watt increments, and either rate them at +3%, +/-5%, +3/-0% or +5/-0%. Solar modules must withstand rain, hail, and cycles of heat and cold for many years. Many crystalline silicon module manufacturers offer a warranty that guarantees electrical production for 10 years at 90% of rated power output and 25 years at 80%. Recycling: most parts of a solar module can be recycled, including up to 97% of certain semiconductor materials or the glass, as well as large amounts of ferrous and non-ferrous metals. Some private companies and non-profit organizations are currently engaged in take-back and recycling operations for end-of-life modules. Recycling possibilities depend on the kind of technology used in the modules. Silicon-based modules, aluminum frames and junction boxes are dismantled manually at the beginning of the process. The module is then crushed in a mill and the different fractions are separated: glass, plastics and metals. It is possible to recover more than 80% of the incoming weight. This process can be performed by flat glass recyclers, since morphology and composition of a PV module is similar to those flat glasses used in the building and automotive industry. The recovered glass, for example, is readily accepted by the glass foam and glass insulation industry. Non-silicon-based modules: they require specific recycling technologies such as the use of chemical baths in order to separate the different semiconductor materials. For cadmium telluride modules, the recycling process begins by crashing the module and subsequently separating the different fractions. This recycling process is designed to recover up to 90% of the glass and 95% of the semiconductor materials contained. Some commercial-scale recycling facilities have been created in recent years by private companies. Since 2010, there is an annual European conference bringing together manufacturers, recyclers and researchers to look at the future of PV module recycling. Production: in 2010, 15.9 GW of solar PV system installations were completed, with Solar PV Pricing Survey and market research company BVinsights reporting growth of 117.8% in solar PV installation on a year-on-year basis. With over 100% year-on-year growth in PV system installation, PV module makers dramatically increased their shipments of solar modules in 2010. They actively expanded their capacity and turned themselves into gigawatt GW players. According to BVinsights, 5 of the top 10 PV module companies in 2010 are GW players. Suntech, First Solar, Sharp, Yingli and Trina Solar are GW producers now, and most of them doubled their shipments in 2010. Top 10 producers: the top 10 solar module producers in 2010 were Suntech, First Solar, Sharp Solar, Yingli, Trina Solar, Canadian Solar, Henha Solar, Sun Power, Renewable Energy Corporation, Solar World. Price. Average pricing information divides in 3 pricing categories: those buying small quantities, mid-range buyers, and large quantity buyers. Over the long term, there is clearly a systematic reduction in the price of cells and modules. For example, in 2012 it was estimated that the quantity cost per watt was about 60 cents, which was 250 times lower than the cost in 1970 of $150. Real-world prices depend a great deal on local weather conditions. In a cloudy country such as the United Kingdom, price per installed kilowatt is higher than in sunnier countries like Spain. Following to RMI, balance of system elements, this is, non-module cost of non-microinverter solar modules make up about half of the total costs of installations. For merchant solar power stations, where the electricity is being sold into the electricity transmission network, the cost of solar energy will need to match the wholesale electricity price. This point is sometimes called wholesale grid parity or busbar parity. Some photovoltaic systems, such as rooftop installations, can supply power directly to an electricity user. In these cases, the installation can be competitive when the output cost matches the price at which the user pays for his electricity consumption. This situation is sometimes called retail grid parity, socket parity or dynamic grid parity. Research carried out by UN Energy in 2012 suggests areas of sunny countries with high electricity prices, such as Italy, Spain and Australia, and areas using diesel generators, have reached retail grid parity. Mounting systems, trackers. Solar trackers increase the amount of energy produced per module at a cost of mechanical complexity and need for maintenance. They sense the direction of the sun and tilt the modules as needed for maximum exposure to the light. Fixed racks. Fixed racks hold modules stationary as the sun moves across the sky. The fixed rack sets the angle at which the module is held. Tilt angles equivalent to an installation's latitude are common. Most of these fixed racks are set on poles above ground. Ground-mounted solar power systems consist of solar modules held in place by racks or frames that are attached to ground-based mounting supports. Ground-based mounting supports include pole mounts, which are driven directly into the ground or embedded in concrete. Foundation mounts, such as concrete slabs or poured footings, ballasted footing mounts, such as concrete or steel bases that use weight to secure the solar module system in position and do not require ground penetration. This type of mounting system is well suited for sites where excavation is not possible, such as capped landfills, and simplifies decommissioning or relocation of solar module systems. Roof mounting. Roof-mounted solar power systems consist of solar modules held in place by racks or frames attached to roof-based mounting supports. Roof-based mounting supports include pole mounts, which are attached directly to the roof structure and may use additional rails for attaching the module racking or frames. Ballasted footing mounts, such as concrete or steel bases that use weight to secure the panel system in position and do not require through penetration. This mounting method allows for decommissioning or relocation of solar panel systems with no adverse effect on the roof structure. All wiring connecting adjacent solar modules to the energy harvesting equipment must be installed according to local electrical codes and should be run in a conduit appropriate for the climate conditions. Standards generally used in photovoltaic modules, IEC 61215, 61646 and 61730, ISO 9488 Solar Energia Euro Vocabulary. UL 1703 from Underwriters Laboratories, UL 1741 from Underwriters Laboratories, UL 2703 from Underwriters Laboratories, CE Mark, Electrical Safety Tester Series. Devices with photovoltaic modules. Electric devices that include solar modules, solar plane, solar pumped laser, solar vehicle, space stations and various spacecraft employ, or have employed photovoltaic modules to generate power. International Space Station, Mir Space Station, Skylab Space Laboratory, Soyuz spacecraft, see also. References